Okay, so today's lesson is about light. It looks like a mind map because it's a really comprehensive lesson. It's got a lot of, I've got a lot of points on the board, but that just means that everything links together. It doesn't mean that it's a very tough lesson to comprehend. So light is just another energy source, just like heat that we were speaking about before. Light is made up of two waves. This is what light is. So when you think about how heat travels in three ways, you had conduction, convection, and radiation. We're now talking about the radiation component. Okay, the light. So light needs two waves to travel. It's got an electric field that travels like this. It's a transverse wave, so that keeps traveling. And 90 degrees to it, you've got another wave that is the magnetic field. So basically, if I'm a light wave traveling towards you, I would look something like this. So something like this. Two waves basically traveling transverse. One is vertical, the other one is horizontal, and they're both traveling towards you. That's what light is. It travels at around 300,000 kilometers per second. That's very fast. Basically, nothing can beat the speed of light. It's the fastest thing in the universe. And if light hits a substance, it's either going to pass right through it, it's either going to be scattered, or it's going to be entirely absorbed. So if you think about any type of material, when light hits a surface, it's either going to pass right through it. We call this transparent. Transparent. If it gets scattered a little bit, it still passes through, but it's kind of being blurry. That's called translucent. So I should write these down actually. Transparent. That's if it passes right through. Then there's translucent. You probably learnt about this in early high school. And then if it doesn't pass through at all, it's entirely absorbed. We call this opaque. So a good example of each one. Transparent is just the window you look at, like your car window that you look through. Translucent is like your shower screen. It's a little bit blurry. You can still see what's on the other side, but it's very scattered. And then you have opaque, like a brick. Basically a wall. So we've covered the properties of light. I'm going to talk about the reflection property of light. So there's a law, we call it the law of reflection, and that law says that if a light ray hits a smooth surface at an angle, it's going to leave that smooth surface at the exact same angle. So if we had a surface like this, and then a light ray is hitting that surface at a certain angle. And by the way, we don't take this angle here. We don't care about that angle. We take the angle between the normal and the light ray. So this angle over here. So what is a normal? Normal just means it's an imaginary line that we draw 90 degrees to the surface. So this angle is basically 90 degrees. So whatever surface you have, the normal is going to be 90 degrees, an imaginary line. We don't really care about the surface itself, we care about the angle between the normal and the light ray. So this angle we call I, angle of incidence. I stands for incidence. I hope that's how you spell it. And then you have the angle that the ray reflects off the surface. That's your surface. This ray, this is the incident ray, and this is the reflected ray. So we call this angle R. And the law of reflection just says that I equals R. So this angle here is going to equal to that angle there if you have a flat surface. It's not too hard. It's just the incident angle is equal to the reflected angle. Whatever surface you have actually, even if you have a rough surface, say the surface looks something like this. It's very rough. Every time it's going to hit, your incident angle is going to be equal to your refracted angle, your reflected angle. So this hits it at that angle, it's going to reflect that way. Sorry, I keep going the wrong direction. And if you have a light ray that's hitting like this, notice how the normal is there. The incident angle is very large. So that's going to bounce off like that, and it's going to come off like that. But So basically, on a rough surface, you're going to have diffuse scattering. And on a plane surface, you're going to have a clear reflection. So a good example of this type of surface is the basic mirror that you have in your home, on your bathroom wall. And this one, when a single light source hits it, the light rays come off in all different directions, and it's all being scattered, it's being diffused. So this would probably be something like the surface of an egg. So you can't really see yourself, but everything is just like, there is no clear image formed on the surface of an egg because it's so rough. So these are the two types of the surfaces that I want to talk about. The law of reflection, don't forget, I equals R. So in the exam, if I say this is 30 degrees, R is going to be, very good, 30 degrees. Or I can trick you and I can say this is 60 degrees, and I won't give you this, and I won't give you this. And I'll say, if that's 60 degrees, find R. Then first thing you have to find is what I is first. I is actually 60 plus something is 90 degrees to the normal. 60 plus something, that something is 30. So your R has to be 30 degrees. You can go over this at home. Moving along. That's done. The law's done, and the mirror image is done. Actually, the mirror image, I want to say something else about the mirror image. Hopefully, if I can run this out smoothly. The mirror, if you have a mirror like this, and that side is the mirror, this is where you are. So you're looking at the mirror from this angle over here, that's your eye, and you're looking at an object, and that object is a candle. So the light from the candle, so let's take the light ray from the top of the candle, that's going to hit the mirror, and it's going to reflect into your eye. Okay? Incident angle, refracted angle. Then let's take an angle from the bottom of the candle, that's going to hit the mirror, and it's going to reflect into your eye. Okay. So your eye thinks that the mirror, the object is actually on the other side, because the eye only sees light coming from this direction. Let's say there was a barrier here and you couldn't see the candle. You can't see the candle. All you can see is these two light sources coming from the candle. So your eye is going to think that the candle's coming from over there. The brain is so smart that you can't assume that it's being bent. It just pretends that these two lines are now somewhere there. It's a little bit hard. So something like this. So your brain will see the object as an image on the other side of the mirror. That's how we actually see stuff. So when you look in the mirror, you see yourself on the other side of the mirror. You can't actually touch it. So the image formed is actually a virtual image. Remember from the previous lesson. Virtual means the image doesn't fall into your world. You're standing over here. There's a wall there behind the mirror. So if the image falls there, it's a virtual image. So that's how we see things in mirrors. Moving along to a new concept called refraction. This is how a lot of things, a lot of technology works. Refraction just means when light passes from one substance into another substance, it changes angles. So as light passes from one substance into another, it changes angles. So when you look into the water, when you're both standing in the pool, and it's like, you know, up to your hips, your friend's legs look very short, and there's a reason for that. It's because the light that's coming off their feet is being refracted. As soon as it leaves the water and enters air, it changes speed because light rays travel slower in water. And as soon as they hit the surface of the water-air interface, that light ray changes, it gains speed, so it changes angles. So it was traveling like this, and then it just starts traveling in a different direction. So you think that the leg is actually higher than what it is. The feet are actually higher than what it is. So that's what refraction is. Try not to get reflection and refraction confused, mixed up. Reflection just means you hit the surface and you get reflected back off. Refraction is when it hits the surface and it passes through, but it changes angles. It's not a straight line anymore. It actually hits the surface and it changes angles. So I'll give you an example of what I mean. You're standing and your friend's like this. That's the water. Your friend's over here. So the light that's coming off the foot of your friend is actually, say you're a bit shorter than your friend, that's the normal. That light ray is actually going to bend away from the normal because it's increasing in speed. So this light ray, this angle of incidence, and this is the angle of refraction. Your angle of refraction, not reflection, your angle of refraction is going to be greater than your angle of incidence. Which means you're going to think that your friend's legs are somewhere here. So what you see is something like this. Where your friend's legs are like that. So you just assume that your friend's legs are short. So that's refraction. Basically, I'm going to give you a little trick to remember the rules for refraction. See how this is water and this is air? They both have their own refractive indexes. Refractive index means how quickly or how easily does light travel through that substance. So air, think about air. You can move your hand very fast in air. But if you're in water, you can't move your hand very fast because it's dense, right? So think about how fast, or how slow rather, air would travel in water. How fast light would travel in water. Light would travel much slower in water compared to air because you can move things faster in air, but you can't move things as fast in water. And think about something even denser like cement or wood or something like that. So every substance has their own refractive index. I'm just going to give you a couple of examples. The refractive index, which we call N, for air is 1.0, which just means everything else relates to that. So the refractive index for ice is 1.31, which means light travels 31% slower in ice than in air. So if I was to say diamond, the refractive index of a diamond is 2.42 rather. That's a huge difference. That's 142%. So it travels much slower in diamond than in air. These are the refractive indices. So rubbing that off, cover that, and two more things I need to cover. There's something, depth illusion. I already did cover that. Perfect. Depth illusion. You think that the depth is shorter than what it actually is because of refraction. And that would mean then that I only have one more thing to cover, and that's total internal reflection. So let's say you've got a fish tank and you have a light source over here. So you shine your first light at this angle and then that refracts slightly away. I still have to teach you that trick, by the way, how to remember if the light ray bends towards or away from the normal. So if I shine, that's ray 1. If I shine my second ray over here, this is water, this is air, that's going to bend a little bit more away. If I shine my third ray over here, that's going to bend even more away. And then I've got this angle that if I shine this angle over here, if I shine this light at this angle, it's actually not going to refract anymore because it keeps getting bent away from the normal. So what's going to happen is it's just going to reflect back in. It's just going to reflect back in. We call this total internal reflection. So total internal reflection, when you think about those, those UFO toys that have these, 100 or 1,000 fibers sticking out, and only at the end of the fibers can you see light. That's what happens. The light keeps coming, it keeps passing through the fiber. It can't escape the fiber itself, but it only escapes at the end because of total internal reflection. Now, hopefully we speak more about this in the lesson. I'll give you more analogies about this in the lesson. But see this angle here, this critical angle, this angle there. Probably can't see it, but that between the normal and that angle of incidence. That angle is actually called the critical angle, or IC. Can you see it? It's a little bit too small. IC. That's a critical angle. As soon as the light stops leaving the substance and it actually starts to reflect at that angle, that is your angle of incidence. So that's total internal reflection. Now the trick that I wanted to teach you in how to remember whether the in refraction, whether the light ray bends away from the normal or whether it bends towards the normal, is how was it? If the light's going to travel faster, it's going to bend away. If the light's going to travel slower, then the light's going to travel, it's going to bend closer. And the way that I remember it is faster is away, slower is closer. So I'll give you two examples. The first example is if I have water and air, so light's traveling out of something. There's a light source at the bottom of your water, your fish tank. Light's traveling at that surface, that's your at that angle, that's your normal. Is it going to bend towards the normal or is it going to bend away from the normal? It depends. Is it speeding up in air or is it slowing down in air? Well, in water, light travels slow. So in air, it's going to travel faster. Faster is away, so it's going to bend away from the normal. So it's going to bend something like that. Okay. Now let's flip the scenario around where if we have say oil, no, not oil. Let's just say somehow we flipped gravity and we've got, how should I do this? No, should be right. Let's just say we're somehow holding a diamond over water. So we know that the refractive index of diamond is higher than the refractive index of water. So if we've got a light source traveling away like that, traveling at that angle, away from the water into diamond, is the light going to speed up or slow down in diamond? It's going to slow down because the refractive index is greater. So because it's slower, it's going to become closer to the normal. And that's the normal. So that's the trick to remember how the light rays actually change directions when leaving one substance and moving into another. Covered. Okay, all good. Hopefully this made sense. If it didn't, please go through this lesson maybe 5 more times.